Hello, welcome to R for Psychology. I'm Dr. Andy Hales from the University of Mississippi, and in this video, we're going to look at how to do a one-sample t-test in R. So let's dive right in, and we'll be using the Tidyverse package as always, and a newer package today called F-Size. So if you haven't already, make sure to install that package, and we can load up both of those, read in the same data file that we've been using. And for today, we're going to be working with a column called estimate, and this represents the number of Skittles that 49 people estimated are in a regular size bag of Skittles. So if we look at our data frame directly and we scroll over, we can see here's our estimate column. The first row shows that the first participant estimated that there's 36 Skittles, the second estimated 33, and so on for the whole column. So we're going to apply a one-sample t-test to this column. So this is the simplest of the t-tests, and this is when we compare the mean of our sample to some known population value or some meaningful fixed point. And we're going to ask, is our sample significantly different than that point? So for starters, before we go doing inferential statistics, we can do some simple descriptive stats. Let's see what the mean and the standard deviation are for our sample. And it looks like, on average, our 49 participants rated an estimated 47 Skittles per bag, with a lot of variance here. We have a standard deviation of 18, so we got a pretty variable sample here. Now, those numbers are fine as far as they go, but of course, a histogram can tell us a lot about the shape of this distribution. And here we see maybe some slight positive skew. For good measure, I went ahead and indicated with dashed lines here two important values. The first is this gray dashed line, and that's 47. That's the mean that we happen to observe in this sample that we drew here. And we're going to compare that to a known population value. In this case, you'll see this dashed red line above the value of 60. Now, I happen to know that 60 is, in fact, the number of Skittles in a typical size bag. So in other words, that's the correct answer. We ask people to estimate the number of Skittles in a bag. They don't know the number of Skittles, but they make their best guess. So this equips us to answer the question, on average, is our sample underestimating or overestimating relative to the ground truth, which in this case is 60. So another way of framing this is, do we have evidence of systematic overestimating or underestimating the number? Running this in R, the hypothesis test is very simple. We just use the t.test function. We supply it the name of the column we're working with. So the name of our data frame is data. So data $estimate is the name of our column. And notice here, this is very important. We have to supply it the known population value that we're testing against. So here I'm telling it 60 is the value to which we want to compare the mean of our sample. And that's mu, as in the population mean. So we're saying here, imagine the population mean is 60 and compare our sample mean to that. And when we run this, we get the t-test output. Now, R knows, based on the type of information we provided, that this isn't just any t-test, this happens to be a one-sample t-test. And right at the top, we have the most important information. We have our observed t-value, which is negative 4.81. Now, you might be developing an intuition for what big and small t-values are, and that tends to seem like a pretty extreme t-value. We have 48 degrees of freedom. This makes sense because our sample has 49 people in it. And then we've got our p-value here. Now, if you recognize that 4.8 is a fairly large t-statistic, you might be expecting a very small p-value, and you would be right. Now, here it's giving it to us in scientific notation. Well, that's because it is, in fact, a very, very small p-value. And so this maybe slightly unfamiliar scientific notation here is just telling us that in order to interpret this number, we'd need to move the decimal place over 5 units to get the actual value. So our p-value is not 1.54. That would, of course, be gibberish. P-values are probabilities. They must be smaller than 1. The p-value is actually 0.0001543. Hopefully I said 4 zeros there. That's the number of zeros there should be because we moved the decimal 5 places. The point is, it's a very small p-value. Now, we have some extra information in here. It restates for us the alternative hypothesis, and you'll notice the alternative is that the true mean is not equal to 60. Notice that that's agnostic about the direction here. So the reason for that is because the t-test sensibly defaults to a two-tailed hypothesis test. We could change that later if we want to. And then helpfully, we also get a 95% confidence interval around our observed sample mean. So we can see here, and we calculated above, our observed sample mean is 47 estimated skittles. And this tells us with the sample size and the standard deviation we have here, we could compute that the 95% confidence interval around that on the low end could be as small as around 42. And on the high end, we wouldn't expect it to be above around 53 skittles. So that gives us some information about how precisely we've estimated this value. Okay, so in this case, we would say that we have pretty strong evidence that our sample was drawn from a population whose mean is different than 60. It'd be nice to say something about effect size, and you'll recall there's two ways we can do that. First is just looking at the unstandardized effect size just in raw units. How different is what we're observing from what we expected? And the way to do that here is to simply take the mean of our sample and subtract from it the population mean of 60. This is just basic arithmetic here. We get a difference of about 13. Now, in other words, let's not overcomplicate this. Our sample underestimated the number of skittles by about 13 skittles. I know what skittles are. That's a meaningful unit. So I think this is a case where the raw or the unstandardized effect size is actually pretty useful on its own. For good measure, let's see what this would look like if we chose to calculate this in standardized units. The measure for that would be Cohen's d. And here we can use Cohen.d, and again, this is from the F-size package that we loaded earlier. Cohen.d, and we give it, again, the name of the column, the known value we're comparing against, and don't worry about y, but we need to tell it that F equals NA. And if you do that, it'll take that 13, that raw difference that we observed, and it will divide it by the standard deviation of our sample, producing a Cohen's d, an estimate of the effect size expressed in units of standard deviation. And here we see that the estimated Cohen's d is negative 0.6869, so on. And you'll see that that is described as medium. Now, recognize that this is in units of standard deviation, so it would make sense to say that our sample was about 3/4 of a standard deviation below the known value of 60. And here, medium is gibberish that I need you to ignore. You may recall hearing or reading at some point that there are benchmarks of what Cohen's d counts as small, medium, and large. Those are without context. They have no meaning on their own. Only you, the researcher, can know whether it makes sense to call something small, medium, or large in the context of your specific research question. So please don't take these labels seriously. It's unfortunate that they're printed. Understand that this is a number that you are entitled to interpret on its own terms. And then finally, while we're here, we also get a confidence interval, and this confidence interval is also a 95% confidence interval, but unlike earlier where what we observed was a confidence interval around the raw mean difference, here we're seeing a confidence interval in units of Cohen's d. So just like before, this confidence interval excludes 0. That's what we'd expect with a significant result like this. But here we would interpret this as saying the lowest Cohen's d that we would expect based on this information is negative 1.28, and the highest we would expect is negative 0.10 if we were to round that. So there you have it. That is how you would run and interpret a one-sample t-test in R.